So thank you for the introduction, and good morning, everyone. My name is Minghan, and thank you for coming to this talk. Today, I would like to introduce our work on energy-aware coverage path planning. So many practical applications require robots to fully cover a given environment, such as for environmental monitoring, searching, etc. But most practical robots are powered by batteries. So they will have limited energy budgets. When the environment is large, they may not be able to fully cover the whole environment in one iteration. So with the energy constraints, we may need to plan multiple passes for the robot in order to fully cover the given environment. And between the two passes, the robot needs to visit the charging station to get fully recharged to continue work. So with the energy constraints, we can ask this question. Should my robot cover further area first, or should I cover the neighborhood of the charging station to minimize the total energy consumption? So this coverage path planning problem by itself is well studied in the literature. So depending on the representation of the environment, the goal could be either to cover a polygon or to cover a graph. Without energy constraints, to cover a graph, it is a well-known traveling salesperson problem. And to cover a polygon without energy constraints, there are also several strategies in the literature, and here I listed two of them. One using a back and forth motion, and the other one uses the spiral-like path. And when working on the graph, some papers study how to navigate from one node to the other with various constraints. For example, here, this paper considers navigate from one node to the other with time window constraints. The vehicle routing problem studies how to cover a graph with various constraints. There is one version of vehicle routing problem called distance-constrained vehicle routing problem, which models the energy consumption by the maximum length of a path. When covering a polygon with energy constraints, it's a relatively new topic. And in the literature, it is mainly done by monitoring the remaining battery level of the given robot. So the paper on the left here uses a multiple robot system. The robot is divided into workers and helpers. When the workers are being charged, the helpers will continue their work. And the paper on the right did similar things to monitor the remaining battery level. When the remaining energy is just enough to return to the charging station, the robot retreats to get fully recharged. So we formulate the problem in this way. We are given an environment which is represented as a polygon. We are also given there is a single charging station in the environment. We also know the energy budget of the robot. Then the goal here is to find a set of passes so as to fully cover the environment and to minimize the number of passes or minimize the total length of all the passes. In this problem, we assume that the energy consumption is modeled by the distance of the robot, the distance traveled by the robot, which means after a full recharge, the robot can move at most b units of distance. Then it has to be recharged. We also assume that in this problem, the robot moves rectilinearly on a grid. So in our previous work, we present a full approximation algorithm for contour connect environments. So what is a contour connect environment? So we say the line in an environment where the cells on it have the same distance to the charging station, we call it a we call it equidistance contour. And we call a cell where a cell is adjacent to the boundary of the environment and it is in the middle of a contour. We call it a split cell. Then a contour connect environment is simply an environment without any split cells. So we call this cell split cell because from a split cell, the contours will break into several segments. Then, in this paper, we study how to deal with more complex shapes environments, and for example, here, the boundary of the environment is more complex and there are obstacles in the environment. So in the literature, there is a TSP split-based approach for K-TSP problem. We can also model this method for this energy constraint coverage problem. So this method first computes a TSP tool over all the vertices of the environment or over all the grids of this environment. Then it splits the TSP tool according to the energy budget. Like the robot follows this tool, and when the energy is just enough to return to the charging station, the robot retreats to get fully recharged. Then the robot go back to the TSP tool and continue following this tool. So let's see how this method works. Let's use B for the energy budget, which is the maximum distance the robot could move after fully recharged. And let's use D for the distance of the furthest vertices or the furthest cell in this environment. So we can also understand D as the radius of this environment. So we know that the robot needs at most D units of energy to go to this TSP tool, and also needs at most D units to go back to the charging station. So each path can cover B minus 2D portion of this TSP tool. So if the total length of this TSP tool is L, then this method needs at most this number of passes to fully cover the environment. And since we know that the maximum length of each path is at most B, so this solution needs at most this number of energy to fully cover the environment. And we also know that the optimal solution will also need at most L units of energy to fully cover the environment. So we can say that this method is bounded by this number of the optimal solution. As we can see, in some cases, this number is good. It can be a two approximation algorithm, but when D approaches half of B, the approximation rate here can be infinite. So let's look at an extreme case to see why it can happen. So for example, for this environment, for the shaded area, the optimal solution will also need to revisit it many times. But the TSP does not consider these revisitings. But opt could be much larger than TSP-based result, which implies that a TSP-based split approach may not be enough to solve this kind of problem. So we need to seek another approach to deal with this. If we view the union of all cells as a set we want to cover, we may be able to find some inspiration from the set cover problem. So we know that the bound of the greedy algorithm for the set cover problem is log n, but the rate just now is not log n. So the question is natural to ask if we can find an algorithm for this energy-aware coverage path planning with a log bound. And that's the contribution of our paper. So we propose a log-D approximation algorithm for this problem, where D is the distance of the first cell in the environment, which is also the radius of this environment. So the general idea of our approach is that we first partition the whole environment into some sub-areas, and then we cover each sub-area one by one. So my following presentation will explain how do we partition the environment, and with energy constraint, how do we cover the sub-areas. First, just now we introduced what is a contour connect environment. Again, it's like we can also understand it as level set problem, level set connected environment, where if two cells have the same distance to the charging station, they are on the same contour. So we can use a sweeping algorithm to decompose the environment into contour connected pieces. We start from the first contour and sweep the environment in distance increasing order. When we meet a split cell where the contour breaks, we form a contour connect environment and start two more sweeping process. Then, after decomposing the environment, we can build a tree representation of the whole environment. where the previously found sub-area can be viewed as the parent node of the newly started sweeping process. With this tree representation, we can define a motion pattern for coverage. That is, first, in terms of the tree, we visit the node of the tree in pre-node. And then in each node, we start from the closest uncovered cell. And from there, we follow the contours. Again, where contours are a line where the cells on it have the same distance to the charging station. And when we found the remaining energy is just enough for returning to the charging station, we also retreat to get fully recharged. Now, can we directly apply this motion pattern to this partition tree? And the answer is not, because some nodes can be very small that can be covered within a single pass. In this case, when the robot transits from node to node in this partition tree, it will lead to many revisitings. So the idea here is we need to group the nodes to form large sub-areas. Here, large means each sub-area should not be able to fully covered by a single pass. We do it by group the nodes from bottom to top. When we find two or more nodes together cannot be covered by a single pass, we group them and delete it from the partition tree until we cover all the nodes. We call the set of these sub-areas as a working zone. Now we can look at more details of our algorithm. So this algorithm just did three things. First, we choose the closest uncovered sub-areas. From there, we follow the contours. And then when we also need to check the remaining uncovered size. So if the remaining uncovered area in this sub-area it can be fully covered by a single pass, we think it is already being fully covered. So let's quickly go through the performance proof of this algorithm. We show that each pass in our solution can newly cover this number of cells in a partially covered area. But on the right side, we also show that for the optimal solution, each new pass can only cover this number of cells. If we compare these two numbers, we can find that our solution can cover at least 1/8 of what optimal can do in the remaining uncovered area. So this will imply a log approximation to this. Why? Let's say n star is the number of optimal passes to fully cover the environment. And since each path in our solution can cover 1/8 of what opt can do, the remaining uncovered area after the first n passes and n plus passes should satisfy this equation. And then we can know that the number of passes in our solution is bounded by this number. And it's also easy to know that if d the radius of the environment, the area of this environment should satisfy this. So now we can get a log d approximation algorithm. So here is a simulation example of what we can do. The first figure is simulating the environment, and then we decompose it into contour connected pieces and build a partition tree of this simulating environment. Then we group the nodes to form the working zone. Again, each sub-area in the working zone cannot be fully covered by a single pass. Then we plan passes to cover the sub-area one by one. And here are the demo of our passes. Different color represents different passes. And I also want to take this chance to show our application of these algorithms. First, the first application is about the first application is for an environmental monitoring project. So this area is chosen from a nature reserve in northern Minnesota, and we use a UAV to fully cover it to detect the objects of interest. And this is the passes we demonstrate. The other application uses a ground robot. So we want to use this ground robot to fully cover a cone field to take data. So one difficulty here is the cone fields are very narrow and it's merely a little wider than the robot size. So the robot needs to fully go through every cone, go through all the cone rows to take the data we care about. And I think this concludes my talk. So thank you all for listening.
Okay, thank you very much, Minghan. Are there any questions? Yes.
Hi, thank you for the talk. Can you, in this approach, somehow penalize the change of the path? I can imagine the path which is consisting of long straight lines, but in this example there was a lot of turns.
Yeah. So yeah, thank you for the question. So in our problem, we model the energy consumption by the length of each passes. So it is true that we should also consider the energy cost by the turning. So that's why actually for this application we use a UAV. While UAV can fly to its four main direction without turning, which to some extent allow us to ignore the energy consumed by turning. But it's true that, and it's also a good research topic in the future, like how can we plan passes to take into this energy consumption. Yeah.
Thank you.
Thank you.
Any other questions? If not, maybe then I have a small question.
Yeah.
So I think the basic assumption that you use is that energy consumption is proportional to traveled distance, right?
Yes.
But I can imagine that in a specific application, the process energy, like vacuum cleaning or mowing, it takes much more energy than traveling alone. So can you take those two energy budgets into your approach as well?
Yeah, I think that's a very good future direction, future research direction. So in my current problem, I think the energy consumption is uniform in the old area, but maybe it's not always the case. So one ongoing project is that we want to build an energy consumption map of a given area so that we can navigate from from A to B with the least energy consumption. Yeah. Thank you.
Okay. If there are no further questions, then let's thank the speaker again.
Thank you.